Hello and welcome back. In example 2, we're asked to design a 1000 cubic centimeter can shaped like a right circular cylinder. Let's jump into it and start drawing a picture of that cylinder. Not the prettiest cylinder, but it'll do. Now cylinders, usually we have a radius and a height. I'm going to just draw the radius and draw the height. We'll say the radius is r, the height is h. We may or may not need them later. It says, what dimensions will use the least material? Well good, we have the dimensions r and h. So we're going to have to figure out what r and h are that will make us use the least material. Now the material that it's talking about, the least material, that means the material that's used to make the can. Not the material, not the stuff that's going inside the can, just the material that's used to make the can. So that's really talking about the surface area of the can. And the least means we're going to minimize. Not minizime, but minimize. Going to minimize the surface area. Now, one of the constraints on this is that we only have a certain amount of volume. So that's going to come into the play later. But for now, what we're interested in is coming up with a function. It could be in two variables, that's fine. We have these r and h variables already. A function that models the surface area, So I'm going to use a for surface area. Some people like to use s for surface area. I'm going to write a for surface area. It'll be in terms of r and h. And if you think about the surface area of a cylinder, let me draw another little part of the cylinder. If you think about the surface area of a cylinder, well, you have the top of the cylinder, which is that circle with radius r. That's going to have an area of pi r squared. But then the bottom is also another pi r squared, so that's 2 pi r squared for the top and the bottom. And then you have that curved surface that's around the sides. So for that, you can take the circumference, which is the distance around the circle, that's 2 pi r, and multiply by the height to get the area of the sides. So take the circumference, 2 pi r, and multiply it by the height to give you the surface area of the curved part of the cylinder. Now this is a two-variable function. This is in terms of r and h. So what we want to do is we want to come up with some equation that relates r and h, that has r and h in it. Now, that's going to be a constraint, and the only constraint we see in this whole problem is the 1000 cubic centimeters of volume. So that's where we're going to start on the side here when we try to come up with this equation for r and h. We know that the volume of the cylinder has to be 1000 cubic centimeters. But then the volume of this cylinder is determined by the formula for the volume of a cylinder. That was real insightful, wasn't it? So what we do to get the volume of the cylinder is we take the area of this circle, which is pi r squared, and multiply it by the height. And that fills in the volume of the cylinder. So that's pi r squared times the height. Or you can just think that's the formula for the volume of a cylinder, at least a right circular cylinder. That's an equation that relates r and h. So what we can do is take either r or h and solve for one or the other. Let's solve for h. H is nice here because long pause. Because there's only one h to replace. Right? This is the only h we have to replace. R is a little bit more uncomfortable because we have an r squared and then we have an r over here. That would get a little bit uncomfortable to solve for the r squared and the r and plug them both in. But we only have a single h to replace, and h is easy to solve for in the equation, so h it is. Notice that now our function for surface area is only in terms of r, so we've completed the third step, which is to write our target function, the surface area, in terms of a single variable, in terms of one variable, in this case r. Let's take a moment to clean up the equation, or the function. 2 pi r squared, looks like some pi's cancel. Someone ate them. Oh, there's an r that cancels. And you've got 2,000 over r. So step 4, maximize the surface area. Minimize the surface area. Minimize the surface area. We don't want to use the most amount of material, we want to use the least amount of material. So we're going to take the derivative of r to start out with respect to r. We get 4 pi r. And then if you take the derivative of 1 over r, you get negative 1 over r squared. So this will become negative 2,000 over r squared. Again, you can rewrite r as 1 over r as r to the negative 1 if you like. So there's the first derivative. Now, what I could do is I could combine this together into a single fraction. So we would have 4 pi r cubed minus 2,000 over r squared. And then we could, if we wanted to, factor out the 4, and we get 500. Not super necessary in this particular case, but if we're used to combining and factoring, it makes it easier to think about the a prime equals 0 and the a prime equals d and e cases. You just look at the top and the bottom. So let's take those cases. A prime equals 0. And a prime does not exist. It's going to be 0 when the top is 0. Which happens when pi r cubed equals 500. So r cubed equals 500 over pi. So r equals the cube root of 500 over pi. Not plus or minus because this is an odd root. Now the d and e case is when the bottom is 0, which happens at r equals 0. But if you think about a radius of 0, that doesn't make sense. That wouldn't be a cylinder anymore. It'd just be a line segment again. That can't be true. So, where's the red? I call it nonsense. So the only r value where we could possibly have a max or a min would be r equals the cube root of 500 over pi. So if we want to talk about our radius, and I said maximum again, but I meant minimum. You know, one question is, you might wonder, how do you know if it's a maximum or a minimum there? What if it's like accidentally a maximum and the minimum is happening at some endpoint somewhere? Well, for these problems, I'm not going to trick you around there too much. They'll be pretty straightforward. Whatever r value or x value that you find, that's going to be the one where either the maximum or the minimum happens based on what you need. But you could always check by plugging in some other x values. If it really is supposed to be the minimum, then you could plug in some r values that are close to this r value, and if you get smaller values, then you know, wait a minute, this is not the minimum after all. So you can check just by numerically plugging in some things, just as a sanity check. So the radius is the cube root of 500 over pi, whatever that number is. That's in centimeters. It turns out to be approximately 5.42 centimeters. But the problem asks for dimensions, plural. So that means not only the radius, but also the height. Now to get the height from the radius, we have this nice equation that we set up. Height is 1,000 over pi r squared. So if we can plug in the r into that, we'll be able to get the corresponding height. Now I'll write out what the height is, and then we'll write out how to find it. So the height ends up being 2 times the cube root of 500 over pi centimeters, which is double the radius. Let's show how we found that. We found that by plugging the radius back into that equation here, 1,000 over pi r squared. So that's 1,000 over pi times the cube root of 500 over pi squared. Now here, oops, it's unfortunate because there's a cube root and it's being squared. Like if we only had one more of these cube roots, the cube root and the power would undo each other and it would open up the 500 over pi. Well, we can make that happen. We can multiply the top and the bottom of this fraction by the cube root of 500 over pi. That way we'll have the cube root of 500 over pi to the third, and the third power will undo the cube root and leave us with just 500 over pi on the bottom. So we get 1,000 times the cube root of 500 over pi over pi times 500 over pi. And now things start canceling. Pi's cancel, the 1,000 and the 500 cancel, and you just have a 2 left over on top. So this is 2 times the cube root of 500 over pi. So we successfully found the radius and the height. One last note, we mentioned that you could numerically check to see if something is really a minimum or a maximum. Just look nearby and see if you have bigger values or smaller values depending on the situation. Another test you could use to check to see if this really is a minimum here is the second derivative test. You can check the answer to your question of how do we know if this is a max or a min there? How do we know we found a min, not a max? So one way of answering that is the second derivative test. Now to use the second derivative test, we need to first off have the first derivative equal to 0, which at this r value the first derivative is equal to 0, so that checks out. And then we need the second derivative. Well, we can go take the second derivative by looking at this first derivative and doing another derivative. We'll get 4 pi, and then the negative 2 will multiply in front and give us plus 4,000 over and then r cubed. So we'll have 4 pi plus 4,000 over r cubed. And notice that that is always positive, concave up, like a cup, which means that r value where the first derivative was 0 corresponds with a minimum. So that's just a little double check. But again, you don't have to worry too much about checking using the second derivative test. Usually if you find an r or an x value, that'll be the one that's either the minimum or the maximum, depending on what your problem is asking for. Thanks for watching this video, and see you in the next one.